Bo Win, and today I'll be talking about the mathematical foundations of BERTScore's text evaluation using the Bible. And the BERTScore is a paper that is written by Jang T, Kishore V, Wu F, and Weinberg K, and lastly Aritzi Y. So this PowerPoint presentation is dedicated to them, and I'm using everything off of their research. So BERTScore. So what is BERTScore? The definition of BERTScore is an emerging evaluation metric for evaluating the quality of text generation models for GPT, RAG, and other NLP/AI techniques. Why is this important? Because right now, especially with the emerging field of AI, LLMs, we want to get our RAGs to work in a way that it doesn't hallucinate. And so BERTScore comes into the picture because it can take a ground truth, compare that to the generated answer, and then what you're going to have is a situation where you have an actual metric to evaluate, is this GPT actually hallucinating, right? And so with that being said, once you get a good enough score, let's say like 90%, you can release your RAG into production for other people to use. And so that's one of the major players of BERTScore. Here's another quick example is that we want to go ahead and for our use case today is we're going to use the Bible as our ground truth to create any more additional translations that can compare to the rational Bible. So here's the BERTScore architecture that I'm gonna go through piece by piece today. So the two key words is a reference and candidate. Reference is basically the ground truth. So the weather is cold today. That's actually the truth. The candidate is freezing today. And what it's going to do is take those two statements, perform the BERT model / tokenizer and everything in terms of generating the actual betting, create that. Then it's going to do a pairwise cosine similarity, meaning that it takes the reference and the candidate and does the cosine similarity between each token. And lastly, it's going to pick out the highest cosine similarity scores and apply these kind of IDF weights. And then from there, it's going to do a weighted average calculation. And then that weighted average calculation is the recall of the reference. So that is a BERTScore overall. Okay. Now let's talk about the Bible. So this is a very sensitive subject, but I want to use the Bible because I feel like personally that the Bible contains a lot of good information, as well as a lot of translations, commentary, sermons, Bible study, everything written about the Bible, people have done a million times over. And I think that using the Bible data set is going to give us the most bang for the buck in terms of finding a BERTScore. So now let's lay out some assumptions. So we're going to use two versions, English Standard Version and the Contemporary English Version. I thought about using King James Version, but King James obviously has words like thou shalt not kill, right? So just before we even look at the whole understanding of BERTScore, if you have words that are more olden terms compared to the relevant terms today, obviously for us to produce something like a good overall BERTScore for today's answers, we'll have to plug in all the old verbiage, right? And we don't want to do that. We want to do something more recent, but it is the standard version, which is ESV. And so we're using ESV, which is the version that most churches use, especially for today's time when they're talking about the truth of religion. They use that Bible version as the truth. Now the other hand is the Contemporary English Version. Let's say you're having a hard time reading the ESV. The CAV is primarily for those who don't understand what's going on in the ESV and want to know more of the context in today's term. They're pretty much the same, but using the same kind of verbiage that we would use today, as opposed to the ESV's more academic language. So the verses that I'm going to use primarily for small examples is Joshua 1:8-9. This book of the law shall not depart from your mouth, but you shall meditate on it day and night, so that you may be careful to do according to all that's written in it. For you, then you will make your way prosperous, and then you have good success. Have I not commanded you? Be strong and courageous. Do not be frightened. Do not be dismayed. For the Lord your God is with you wherever you go. So that's the truth. That's the reference, and the candidate verse is, long ago I promised the ancestors of Israel that I will give you this land to their descendants. So be strong and brave. Be careful to do everything written everything my servant Moses taught you. Never stop reading the book of the law he gave you. Day and night you must think about what it says. If you obey it completely, you and Israel will be able to take this land. Now, before I start anything, there's a good video by Danny Chang that talks about cosine similarity. I'm gonna brush over it a little bit just because I want to focus more on the BERTScore, not cosine similarity, even though it uses cosine similarity. So cosine similarity is the cosine angle between two vectors. In our case, where our vectors are going to be these embedding vectors, which are just high dimensional vectors. So what it does is that it takes A and B, does a dot product of two vectors, and then takes the Euclidean norms of the vectors and divide by that being multiplied. So moving forward, so when you have a dot product, so the dot product of our use case here is going to be a dot product of A and B. What is A and what is B? So A is going to be a small embedding. You look at the code here. I'm just using the ESV embedding of that verse, Joshua 1:8-9, as well as doing that one as well for the CEV version. Again, if you see here, you see the bracket 0. I'm just taking the first vector. There's multiple vectors going on, but I just want to do a simple example using the first vector so that you can see the multiplication between the two. Now, with that being said, so once I do the coding of that, so what it looks like is doing the real dot product. So you dot the first ESV first token, the CEV first token, and when you multiply that together using Python library, the dot product, you get 3066.7021 as your answer. Now that's how you do dot product. So now let's say I compute the norm. So I'm going through the full cosine similarity between the first two vector tokens. So to compute the Euclidean norm, use this Pytorch library .norm, and then you just take the dot product divided by the norm being multiplied against each other to get your cosine similarity between the two. In this case, our cosine similarity between the two is going to be 0.933. Now, just to do comparison to the other library packages, so what I did in the math calculation, getting the output value of 0.933 is compared if we use sklearn or Pytorch. And so with that being said, there's two different ways of doing it. You can compute the Pytorch numpy arrays and do the subtraction of compute sign. They use the scipy array of doing that. The other way is the same thing, convert it to numpy arrays and reshape the vectors. Now let's take it and move it a little further. What we're going to do is now talk about what's really going on if we took those two verses. So we're going to use something called matrix multiplication. So matrix multiplication, the reason why we're using matrix multiplication is because we're measuring the cosine, the angle between vectors in multi-dimensional space. So it's not going to be one vector, it's going to be a high dimension of vectors. And so with these many vectors and high dimensions, we have to use matrix multiplication. So in PyTorch, what that is mat mule, and then what we're going to use is .get to do the normalization process as well. And so a couple of things to note. What this means in actuality is that we're taking each word or each token word and comparing it to the other candidate reference. So what that means is that in math terms is that we're going to do a full matrix multiplication and then taking their norm product to get that answer. So we're going to divide, we're going to do a lot of like cosine similarity between a lot of different vectors at the exact same time. So again, this is a couple big things is that we're going to compute all the dot product for all pairs. Now, once we get all the cosine similarities of doing the dot product dividing by the norm product, we're going to have these a matrix full of these kind of cosine similarities, right? So the purpose of the maximum similarity is to find the ones that have the best matching token in terms of candidate to reference. And so what that means is that why we're doing this is we can have the highest contextual meaning, the highest token alignment, um, as well as the power to be robust and paraphrase if there's multiple meanings inside one word. Um, there is an easy way to do this. All you gotta do is type in .max on Pytorch, and it'll give you all the highest dimensions of that, or the highest cosine similarity of that. And our use case here, so the left-hand side graph talks about the weather is cold today. It is freezing today. That's a simple example given this right here. In our use case, once we do the cosine similarity of those two embeddings, specifically the embeddings for Joshua 1.8 on ESV and CEV side, you see that how it looks like in terms of that is pulling the biggest weights from the row of vertex, the vectors. And so here I made red boxes around them to show you that these are the maximum cosine similarities in that vector. Now the next part is, if you look on the next part of the graph here, you see the word IDF weights. So IDF weights represent inverse document frequency. So here we're going to find the most frequent words. IDF has an actual equation which is equal to log divided by n, log of n divided by nw. And so what that means is that it's a statistical measurement of how important a word is to the document, or the frequency of the word across multiple documents. So what the IDF does is that it adjusts the similarity scores to emphasize more semantic weights, especially words that mean more than others. A good example is like love. Love is always appear multiple different times in the Bible. It has different meanings, like God is love. Um, so that is something that's very important to the Bible. But other things is God loves you. That's a verb as well. So that's a lot of different ways of going at it, which IDF helps to account for. So to get the IDF weights, it's pretty simple if you follow the exact formula. So if you have the word, so you take the log of the word divided by the number of words in the count. That's going to give you the actual log frequency. So it's a pretty simple formula you can plug in and get most of the words, the IDFs. Next thing is getting the importance weighting. Now the importance weighting is a very important feature of the next part of our architecture. Is we're going to get the recall metric, and the recall metric is just the 1 divided by the magnitude times the sigma of the maximum cosine similarity score on the transpose multiplied by the IDF weights. And so what's that gonna do for us is we're gonna go ahead. I'm gonna use this as an example because if I did it for the others, it's gonna be a little more complicated. So um, you take the highest cosine similarity, okay, and you just basically weight averages. So you take that multiplied by the IDF weight, add that to the next biggest cosine similarity. It'll have its own weight as well. Multiply those two together, and you keep continuing on forward and forward until you get a sum combination of those multiplication. Then you divide by the sum of the IDF weights. And so when you do that, it's going to give you a number of 0.53. Now, once you have the BERT score, so BERT score in retrospect, our BERT is the recall score of doing the pairwise similarity to maximum similarity to applying the IDF weights. Using the weights from the reference, that is going to be the recall. If you use the precision precision of the BERT, that's going to be on the candidate. And so, with that being said, how we're going to do this in the full natural nutshell is calculate the pairwise similarity. Once you calculate the pairwise similarity, you're going to go ahead and apply finding the max of those cosine similarities. After you find the max of the cosine similarities, you're going to go ahead and use your reference IDF weights and multiply against that again with the maximum values. And then You sum those up and divide it by the sum of the reference IDF weights. Now, if we do this by hand using the BERTScore, I wish I was a little closer. My scores were a little bit off. They were about, the highest one was 0.74. If I use the Arthur's package that you pip install by doing pip install BERTScore, it gives you around the score of 90. So I'm losing about 16.16. I'm not sure why. As I was doing research and spent multiple hours trying to really think through how I can't get 0.90, one of the biggest things, the way you calculate the IDF weights. There are multiple ways you can calculate IDF weights, but in particular, I'm using two documents to get the IDF weights. In actuality, they're looking at the term frequency of more bigger data sets, but there's like different ways you can go at it. There's like probabilistic IDF weights, smooth IDF weights. So how they use the IDF weights plays an important role. So one of the things I did was go into the author's package and try to understand where the IDF weights play into, but it was really hard to understand that. My best shot was about 0.74 by doing a lot of research to tweak out the IDF weights. One of the biggest hiccups was getting the same um, vector size when it comes to the transpose, and when you multiply for the cosine similarity, maximum cosine similarity multiplied by the ref IDF weights, it did not play out well. You can't. It always was a 92 against a 94, and it didn't multiply if the vectors weren't the same. Because how the tensor worked was that it started off, the first number in the tensor was 94, and then it ended on a 94, but the IDF was just a 92. Um, so with that being said, some things I learned from doing hand calculations were a lot. So how the IDF weights played a role, as well as how I would think BERTScore would increase if I change certain numbers, right? And so one of the biggest things that I think I got from just doing the BERTScore comparison, just playing with the IDF weights was as well as the cosine similarity, is if you increase the term frequency of the matching, so a lot more words that are matching in terms of term frequencies to the IDF weights, that will help increase your BERTScore. And I will talk more about that in the next slide. So I call the next slide the boosters. And so just a quick experiment. I want to just do more than just learn the mathematical formula. I want to use that kind of background knowledge to increase my BERTScore as well as get a better BERTScore. And so first thing I did was I went ahead and just kept using the author package. I compared ESV to ESV. Now ESV to ESV is going to be a precision of 1, right? Recall 1, F1 1. So that's our standard. So it knows that works well. Now let's say we do some small experiments. Let's say just doing some quick math. What would happen if I increase the IDF weights, right? If I increase the IDF weights, if we had the baseline score of 0.7534, increasing the term frequency still increased the actual BERTScore, but it didn't increase it by that much. If I decrease the term frequency, it actually went up by a larger margin. But again, I didn't take account that maybe I'm not using the same amount of magnitude, right? I just made it all 4s for the IDF weights with just keeping the same decimal. Here I kind of did a random sampling of like, I'm going to add 3 here, add 2 here kind of situation. So it could be just a magnitude of difference. Still not sure, but again, in overall scheme of things, it doesn't really matter what the IDF weights is. It changes it just barely. Now, the biggest significant increase is actually changing the cosine similarity. So in this case here, if you look here, I changed all the cosine similarities to be in the 90 range. And when I did that, it gave me a good cosine similarity score. So, or BERTScore. And so that being said, the biggest player of this is probably increasing the amount of embedding vectors, and then from there multiplying that by the dot product divided by the norm product is going to play a big difference. And so the amount of vectors, how the vectors are in the space, how it's tokenized, plays a big role into that. So this is no, my last slide talks about just the full overarching like application. So this is something I really enjoyed performing because it allowed me to take what I've learned from my math side of understanding the BERTScore and applying it to a real situation. So here's the experiment. Can we make a new and better CEV version Bible by using the BERTScore? So again, if you compare the ESV, ESV to ESV is 1. The other one's ESV to CEV only has like a 9% BERTScore. So it captures about 90% of the quality of the real text. Can we have a better score? So what I did was I did some prompt engineering. I took my CEV or I fed it the ESV version. Then I prompted to create a contemporary version of the text while retaining 100% of the term frequency involves using the same key terms but in a modern context or with updated language. Here's at contemporizing the given text. So when I did that, that prompt gave me about a 0.87. So I was close, but not no CR. So what I did was I went back and try it again, but now keep all the words the same. See how it says keep all the words the same? That deals with more of the cosine similarity because those words match up with that word. We need a dot product divided by the norm product, but rearrange it so it can be in contemporaries. So rearrange the words in a certain way that it can, provide that IDF weights for today's generation. And so when I did that, it gave me about 0.94, which is better than the CEV version. So if I took the GPT that gave me this answer and applied it to the rest of the Bible, I could probably create a better version of the CEV than the CEV now, which means that the CEV version now can be replaceable for a better version, and it doesn't take much to do that by using a language model, and that is significant because that could replace somebody's job, or this is a new tool for the Bible creators to make a new version that can be just as accurate without having a PhD. And so that concludes my presentation. Thank you guys so much for everything. Hopefully that can help out. Sorry if it was kind of rushed, but if you have any questions, this is my contacts, LinkedIn. So thank you.